Hello everyone, this is Dr. Zach. Today we're going to use the ratio test and the root test to determine whether our series will converge or diverge. Take a look at your lesson preview. For this problem, you should be reminded to use the limit as n goes to infinity of f to the n over n to the fourth before you do anything else. So make certain you are using your nth term test. Try the same thing with question B and see if you can tell if this is a convergent or divergent series. Today we're going to discuss the ratio test. If we have the series a sub n with non-zero terms, our series will converge absolutely when we take the limit as n goes to infinity of the a sub n plus 1 divided by a sub n is less than 1. Now our series will diverge if our ratio is greater than 1, or if it goes to positive infinity. Unfortunately, the ratio test is inconclusive if the ratio is equal to 1. You're going to have to find a different test to use. As we look at example 1, notice we have n factorial. Because of that n factorial, it's challenging to use one of our previous tests. So let's try the ratio test. This is actually my favorite test. We'll take the limit as n goes to infinity. We want to have the absolute value of our 2 to the n plus 1 divided by n plus 1 factorial. This is all over 2 to the n over n factorial. We want to do our algebra to simplify this problem. We'll have the limit as n goes to infinity, 2 to the n plus 1, keep your absolute value, over n plus 1 factorial, multiplied by the reciprocal, n factorial over 2 to the n. Simplify, we will have the limit as n goes to infinity, absolute value of 2. Now, look at your factorials, please. If the numerator is n factorial, that means n times n minus 1, and it continues until you get to the value 1. In your denominator, we have n plus 1 times n minus 1 until you get to 1. Understanding that will tell us everything in the numerator cancels, and your denominator is going to be left with 2 over n plus 1. Rewrite the problem again. We have the limit as n goes to infinity of our absolute value 2 over n plus 1, which is equal to 0, which is less than 1. And that tells us, of course, that our series is convergent. And it is actually absolutely convergent. When we look at example 2, the exponents are what's causing trouble for this problem. What we will do is try the ratio test. Take the limit as n goes to infinity. We will have the quantity n plus 1 squared times 2 to the n plus 1 plus another 1 divided by 3 to the n plus 1. We're going to divide by the original sequence. However, that's going to be multiplying by the reciprocal. So we have 3 over n times n squared, 2 to the n plus 1. Now we're ready to simplify this limit. We will have the limit as n goes to infinity. And as we simplify, notice we will have 2 divided by 3, and for the n plus 1 squared over n squared, those have an equal amount of exponents for your n plus 1 squared over n squared, so our limit is equal to 2/3. Now 2/3 is less than 1. From the ratio test, our series will converge. Give questions 1 and 2 a good try. Now it's time to take a look at the root test. Your series is going to converge absolutely when the limit as n goes to infinity of your nth root is less than 1. Conversely, if your series will diverge when the limit is greater than 1 or heading towards infinity. And again, our root test is inconclusive when we have the limit as n goes to infinity of our nth root equal to 1. When do we use that root test? Take a look at example 3. Notice we have exponents that include n. So this is our indication that we want to use the root test. Take the limit as n goes to infinity, the nth root of e to the 2n over n to the n. When you take the nth root, it's going to simplify our problem to become e squared over n. Now the limit as n goes to infinity, e squared over n is equal to 0. And since that is less than 1, we know from the root test that our series will converge absolutely. Take a look at example 4. Again, we have the exponent n, and if we use our root test, the limit as n goes to infinity of 4n minus 3n cubed over 5n cubed plus 1 raised to the nth power, but then we take the nth root of it. That will cancel out those exponents. And you can see the limit as n goes to infinity in dropping your lower order terms becomes 3/5, negative 3/5, n cubed over n to the third. Did you notice I was sloppy about my absolute values? Let's put that absolute value into the problem so that we can see that we have 3/5, which is less than 1. Therefore, from the root test, our series will converge absolutely. Go ahead, give questions numbers 3 and 4 a good try. Complete these last 4 questions. Afterwards, you can check your answers.